This is Math 265A, Cuesta College. I'm Joe Vasta, and we are going to cover 5.3, the fundamental theorem of calculus. So it sounds pretty important, and it is, and we actually already covered the fundamental theorem of calculus when we were talking about bugs. So let's go through this and then show you that it's the same thing that we were doing before. If f is little f is continuous on a closed interval AB, and big F is any antiderivative of little f on AB, then the net area, this was our definite integral from a to b of f of x dx, equals the antiderivative f of b minus f of a. So, very important theorem in calculus, and you might have noticed that I didn't say anything. This is called the fundamental theorem of calculus part 2. Why am I not doing part 1 first? Because this is the most important one. This is the one you're going to use all the time. So we will go over fundamental theorem of calculus 1 after we do a few examples. So what does this say? All this says is, remember what this is right here. This is the net area of the velocity graph in a time interval. Let me just write that down. So this right here is the net area of a velocity graph in time interval AB. Okay, so that's what that was. It's the net area of a velocity graph, net area of any graph, but I'm just going to go ahead and say velocity. And what does this happen to be? Well, this happens to be the displacement of the bug from A to B. And so that's what we said when we were going over the bug. I think it was bug 13, or it could have been earlier. The net area of a velocity graph in the time interval is actually equal to the displacement over that time interval. And so that's really the real motivation for me for the fundamental theorem of calculus part 2 is that. But fundamental theorem of calculus part 2 says that we can evaluate a definite integral without doing approximations with rectangles. We can actually just take the antiderivative and get the whole net area just by evaluating the antiderivative at the endpoint, subtracting, and that computes a whole area or a net change. Let's go ahead and do some examples. We've been rambling on about this long enough. So let's see if I can find my examples. Oh, here they are. So here's example number 1. So in your homework, you're going to get a whole bunch of these. Evaluate. So evaluate the definite integral. This is called a definite integral. Let me contrast that, and I wasn't planning on doing this, but you've already had problems where you were evaluating something that looked like that, and that's the indefinite integral. See the difference? This one has numbers there, and this one does not. This just means find the antiderivative of 3. This is saying find the net area of 3. And we'll even draw a picture on this one. So what we do, I'll come back and do the purple one after, is the fundamental theorem of calculus says to do this. We take the antiderivative of 3, which is 3x. Okay? And then, this is the notation for it. We evaluate this at these two numbers here. So what the fundamental theorem says is we evaluate this guy at 7, and then we subtract. So this is what's reminding me of displacement. And then we evaluate this function right here at -2. So let's see what we get for our answer. This is 21 plus 6, which is 27. Okay, so that is the answer to this problem. And we could have put 3x plus c, but you would have had the plus c here, and then we would have subtracted the c on that. So you can take c to be whatever value when you're doing definite integrals. We'll come back and draw a picture on this, but I want to show you the indefinite integral. It's just the antiderivative of this, so this would be 3. I'm doing it in blue now. 3x plus c. And so that is the indefinite integral, which just means find the antiderivative of that, and there it is. Okay, so this is the definite integral. What does this mean? This means the net area. I'm going to go ahead and draw this graph. In your homework, they're going to have you do this a few times, so I might as well do it on this one and maybe another one. And so here's x, here's y. My original function says y equals 3. So 1, 2, 3. We're going from -2 to 7. So from -2 is like right here, 7's right here, and I'm finding this right here, the net area. And in this case, since it's above the x-axis, this whole thing is going to be a positive area. And you can actually see that it is 9 times 3, base times height, which gives me the 27. We were doing these definite integrals using geometry, I think in the previous section, but now we can do these using antiderivatives. And you might say, well, I like the geometry better, but on the next problem, you won't really be able to just take the area of a rectangle or a triangle. It would require a lot more if you wanted to do it geometrically. So there is the problem number 1. Let's go ahead and do a few more problems here. Here's problem number 2. So we are finding the definite integral. So sometimes we'll say the integral from 8 to 27 of this function, cube root of x. And so what we want to do is take the antiderivative of this. So our first step that we're going to do is rewrite the cube root of x, so it says x to the 1/3 power. And then that I can do the antiderivative of using the power rule for antiderivatives. So this gives me x to the, I add 1 to that, 4/3 power, and then I divide it by 4/3. And I can take my c to be 0, and let's go ahead and put this up here. So this is kind of weird, you got to get used to this notation, 8 to 27. Now, before I evaluate this function here at 27 and 8, I think I'm going to rearrange this. I'm going to do a copy dot flip, because the top is over 1 and the bottom I'm going to flip it. And so when all that is done, I end up getting 3x to the 4/3 power all over 4. This gets evaluated from 8 to 27. Okay, so we'll bring it up here. And here's the fundamental theorem of calculus. To find one of these, you take the antiderivative, you evaluate it at the top number, and then subtract the evaluation at the bottom number. So this is 3 times 27 raised to the 4/3 power all over 4. And then we have minus 3. We're going to evaluate it at 8 times 8 to the 4/3 power all over 4. Okay, so now let's figure out what this is. The cube root, so that's what the 3 means, of 27 is 3. 3 to the 4th is 81. And so let me just write out this middle step. So this is 3 times 81 all over 4 minus 3 times, we'll do the same thing here. The cube root of 8 is 2. 2 to the 4th is 16. So then we do the calculation of 81 times 3. I'm getting 243 over 4 minus 16 times 3. That's 48 over 4. Now they all have the same denominator, and so what I can do is go 243 minus 48. That gets me 195 all over 4. So anytime you evaluate the definite integral where there's numbers there, you're going to get a number for the answer. You're not going to have a plus c or anything like that. Had we just evaluated this without those numbers and did the indefinite integral, our answer would be this guy right here. Without that, plus a c. Okay, so I mean, if you like, you could write that as a mixed number, and that's, I think it's 48 3/4. I could be wrong on that, so I'm not going to box it because I'm not super confident on that. And this gives us the answer to problem number 2. I'm not going to go ahead and draw a picture on this one. Maybe I'll draw a picture on the next one. And let's do problem number 3. Maybe you can do number 3 on your own by pausing the video and cranking out the answer to that. Okay, so I've got to take the definite integral of this function here. Okay, x minus 3, x plus 3. So the best thing to do, because I have to do an antiderivative, is to multiply that out. And that's a difference of squares. So this is going to give me integral from 2 to 3 x squared minus 9. So what we like to do when there's more than one term, when your integrand has more than one term, is we like to put parentheses around those. And then we have the dx there. Okay, so technically we really still are doing things where this is really a height times a base, and we're taking a limit, and you know, there's always things going on in the background. And if you become a math major or take higher math classes, then you can prove more things. But right now, let's just go ahead and do this the simple way, maybe without thinking of all that. The antiderivative of x squared is x cubed over 3. The antiderivative of negative 9 is minus 9x. Okay, because we have two terms there, I'm not going to put the plus c because I'm doing a definite integral, but because there's two terms there, I'm going to go ahead and put parentheses there, and then we'll put our evaluation line. I'm going to evaluate from 2 to 3. Okay, so first I put 3 in. So this is 3 cubed, that's 27 divided by 3, which is 9. And then I put 3 in there, so 9 times 3 is 27, so this is minus 27. And that's putting 3 into this function here. Now I'm going to go ahead and put 2 into the function. Now when I put 2 into the function, I got to remember to go minus that. So this is going to be 8/3 And then we have minus 18. Okay, so here's the evaluation at 3, here's the evaluation at 2, I'm subtracting. And really getting back to the bug, if that was the velocity, all I'm doing is computing the displacement of the bug on the number line. Let's go ahead and distribute the negative. So I have 9 minus 27 minus 8/3 plus 18. 18 plus 9 is 27, and you have a minus 27. So it's kind of, I could have put it down here, but I'll just put it up here because why not? This is negative 8/3. And I know some of you are thinking, wait a minute, Joe, wait, areas can't be negative. Well, this is a net area. So it adds up all the area. The stuff that's above the x-axis gets positive, and the stuff that's below the x-axis gets negative. If in your homework you were doing one of the problems where it asks you to graph the integrand and display the net volume, this is what we do. Let's see if we can do this problem here. There's the x-axis, the y-axis. So here's x. Here's y. I'm graphing this right here. I'll put it right down here. Y equals x squared minus 9. So it looks like it's a parabola that gets shifted down 9. And it also has x-intercepts at 3 and negative 3. So I'm just going to go ahead and freestyle this one here. Oh, okay. Doesn't look very symmetric. Okay, so what are we doing? We are computing, so this is 3, and this is negative 3. So the scaling on my negative x-axis is different than the scaling on my positive x-axis. And I don't know why they hired me to teach math if I'm doing junk like that. Okay, I'm evaluating from 2 to 3, so here's 2 on the x-axis. And what that's going to be, look, from 2 to 3, all the graph is right below. So watch this. So we have this right here. So unlike that other one, problem 1, where it was all above, this is all below. Now, this would be very hard to compute the area just using geometry. And so the area, the net area, well, the area of that red thing is 8/3. So the net area, because it's below the x-axis, is negative 8/3. And so that completes problem number 3. We're not always going to draw pictures. I think on the next one I do want to draw a picture because it's kind of neat. But then we'll stop drawing pictures after a while. Okay, let's go ahead and do another problem. And some of you are thinking, well, what is the fundamental theorem of calculus part 1? What does that have to do? We'll get to that. Let's take the integral from 0 to infinity. And did I say infinity? I meant from 0 to pi. We're taking the integral from 0 to pi of sine x. The instructions are evaluate. Let's see if we can do this. And the reason I'm kind of keeping the examples basic on 1 through 4, just, you know, if you've never seen this before, we want to take baby steps into this so you get comfortable with this. Okay, well, what is the antiderivative of the sine? The antiderivative of the sine is negative cosine x. Okay, and we are going to evaluate this from 0 to pi. Okay, so we have to be careful because our function says negative cosine x. So when I put a pi in there, I'm going to get negative cosine pi. I'll put parentheses here. And then when I evaluate this at 0, I get negative cosine 0. And then there's a minus in between. That is the fundamental theorem of calculus, where you take the antiderivative and do those two evaluations and take the difference. Okay, so cosine of pi, if you remember the graph, you know, it starts off at 1 and comes down, dips down. this is actually going to be, so there's a negative there. This cosine of pi is -1. Okay. So this guy right here is that. And then we have minus, and in here we have negative cosine 0. And of course you could plug these into your calculator, but what's the fun of that? The cosine graph starts off at 1, so cosine of 0 is a 1. So this guy right here is 1. I know it's easy to get lost with all these negatives. So really I have this intense calculation of 1 plus 1. So the answer to this definite integral is 2. And even though we didn't, I said I was going to try to stop drawing pictures, I want to draw a picture on this because this is really cool. We have this trig function. It's the basic trig function. It's the sine of x. And so we have, it goes like this. It goes up like that, down like that, and it just keeps going, and it keeps going this way. Here's 0, here's pi, here's 2 pi. And so I remember when I first saw that, I was like, wow, that's kind of cool, and it just keeps going. But I never really thought about, like, hey, what is the area? That's the wrong color. I think I'll do blue. It's the area from 0 to pi. So here's 0 and here's pi. It's actually a positive net area, and it's, I didn't know this until I took calculus, but the area of those little things happens to be 2. See, so the area of that blue thing is 2, and I didn't know that. That was kind of cool because you have pi's and 2 pi's everywhere, and then this goes up to 1. So let's go ahead and do this. This is just a bonus, so you don't have to pay extra for this. I'm going to go ahead and do problem 4.5. It's going to be really quick. So if I went from 0 to 2 pi of the sine of x. I'm not going to go ahead and do the calculus on this, but maybe you can tell me what the answer is, or you can't tell me because you're just watching a video. But look, if you go like this, you've got an area of 2 there, but then you've also got an area of -2 down there. And so if you sweep across from 0 to 2 pi, that definite integral is going to be 0. Okay, so that is, let me go ahead and draw this right here. That's for problem 4.5. Now, why would I go 4.5 and not put a 5? Because I kind of planned things out, so that would have ruined this problem right here. So let's go ahead and do problem number 5. Maybe you can do problem number 5 on your own. Maybe you can't. I don't know. You pause the video if you're going to. I'm going to go ahead and evaluate this definite integral of this function. Now, this looks pretty bad. So what I want to do with this is I want to split the fraction. So this equals the integral from 1 to 2. This is 2x squared over x cubed minus 4 over x cubed. And then there's 2 terms there, so I'll put parentheses around there and put a dx. Okay, so look what we have here. We have 1 to 2. This is 2 over x. And then this one's going to be minus 4 over x cubed. So because these are antiderivatives, I can break this up into 2 integrals, because the integral of a difference is the difference of the integrals. I'll just keep them in here and just deal with them separately. This is a common thing. So some of you may want to just skip this step, but this is a common thing that people do when they're first learning this. They go, oh, well, I have to do the power rule, and then you go like this: 2x to the -1, and then you go minus 4x to the -3. So you're thinking to yourself, well, let's go ahead and do the power rule here, and then you replace that, you add 1 to that, and you go, oh, -1 plus 1 is 0, and then you divide by 0, and then you're in trouble. So there's your sad face. There's some tears. Maybe we should put some hair on this person. Hey, look at that. How many times have you sat in a math class? You look like that. Look at that. This is me. This is me in English class, especially when they start getting all political. And I'm like, I don't know why my chin is really big. Well, anyway, wow. So this was bad. We didn't want to do the power rule on this. Now we'll want to do the power rule on that, but here's the one that you cannot use the power rule on, and we should have kept it as 2 times 1 over x or 2 over x. And hopefully you remember what that one is. So this is the integral from 1 to 2. Let's go back to this, 2 over x. But we'll keep the other one like this, minus 4x to the -3 dx. Okay. So if you remember correctly, the antiderivative of 2 over x, well, the antiderivative of 1 over x is the ln absolute value of x. So this is going to be 2 times the ln absolute value of x. And that is the only one that will not work with the power rule. Everything else, you'll get some number in the denominator that won't be 0. Like this one here. So watch this. This is minus 4x. So we add 1 to -3, so this is going to give me a -2, and then you put the -2 on the bottom. There's 2 terms there, so I'm going to put parentheses. This is going to get evaluated from 1 to 2. This right here is the notation. We are doing the fundamental theorem of calculus every time you evaluate a definite integral. Okay, so let's go ahead and do more stuff here. I put 2 into this function. Or, you know what? I think I'm going to simplify this first before I plug those numbers in there. So this is 2 ln absolute value x. And then I'm going to have a plus, because there's 2 negatives there, I'll have a 2 over x squared. Okay. Now that could have been a big mistake because I'm running out of room here. I'll have to get another piece of paper. Okay, I put 2 in for x. When I put 2 in for x, I get the absolute value of 2, which is 2. So this is 2 ln 2. And then we have plus 2 over 4. Then minus, that's the fundamental theorem of calculus working here. I'm finding a displacement. And then I put 1 in there, so this is 2 ln, absolute value of 1 is 1, and then we have plus 2. Okay, so this is 2 ln 2, and we have plus 1/2, and maybe you remember the log graph, but the ln of 1 happens to be 0, so that guy's out of there. And then I have minus 2. So I'm almost done actually computing this. I just have to go 1/2 minus 2. So this is 2 ln 2 minus 1/2 minus 4. 4/2 gives me a -3/2. So there's your answer. And this is a number. This is a net area of this graph from x equals 1 to x equals 2. And of course, you know, this is just your luck. You'll be doing your calculus homework. And then you look in the back of the book, and they'll have ln 4 minus 3/2. Ha ha ha. And I think they do that just because they realize too many students are coming through calculus and they just want to upset people. So they just did the power rule of logarithms where that 2 jumps up and becomes the exponent. So just want to warn you, I say this in lecture just, so you're on guard, so you don't just shred your homework once you see just the slightest variation in your answer. You could have got the right answer, and they could have just used some algebra of logs. So there it is. There you'll get homework problems like this. I think we should do a few more of these, and then we have to get to the other part of the fundamental theorem of calculus, which is actually part 1. So if you remember, when we started off, we every time we do a problem like this, this is the fundamental theorem of calculus, and our book calls it part 2. Now, the fundamental theorem of calculus kind of brings this up to the point. It says, for this to work, we have to have these conditions, and we really haven't been checking them on every problem, and so maybe we should have, or whatever. It says f is continuous on the interval. Okay, so we'll stop right here. Look at this one right here, from -1 to 1. Is this function f, 1 over x squared, is it continuous on that interval? And the answer is no. So what are we going to say about this? We're going to just say it does not exist. Okay, now we'll deal with things like this perhaps in the next calculus class. And I'll write why. This is an infinite discontinuity. Oh, that's the last thing I want to write out, so I'm going to abbreviate it. This doesn't say infinite disk, but it's an infinite discontinuity at 0. And then we're done. Did they give you any like this in your homework? No. Other books will, just to see if people are paying attention, but I think our book gave you the definite integral of functions that you can take the definite integral of. Now you can take the definite integral of this guy if it was from 1 to 5 or -7 to -6. But when this interval includes 0, then we just walk away from that. Let's go ahead and do another problem. This will be the last definite integral problem we do. Number 7, oh, everybody's favorite, because it has trigonometry. Okay, so what am I going to do with this? I'm going to go ahead and rewrite the integrand. This is 0 to pi over 4. And multiply that secant through, so I have a secant squared x, which I think I know how to take the antiderivative of. So if we remembered our rules, you'll go, oh yeah, I know what that one is. It is the tangent. Now this one right here, when you go secant times the cosine, remember what the secant is. The secant is really 1 over the cosine. So you're going 1 over cosine times the cosine. That's really cosine over cosine, which is 1. So it was well worth multiplying the secant through, distributing it. And so what I'm going to do is throw some parentheses up. Now if you're taking higher math classes, sometimes they abuse the parenthesis rule with integrals. And that's, when you get to a higher level and the teacher stops putting the parentheses there, then that's alright. But for now, we're going to do that. Okay, let's go ahead and take the antiderivative. We are doing the fundamental theorem of calculus. The antiderivative of the secant squared is the tangent x. The antiderivative of 1 is just x. And once again, on this one, let's go ahead and put plus c in there. I mean, we could put whatever c value, but we really shouldn't do this usually when we do this. I just want to, for those of you who may have missed the other lecture, you're like, why don't you put the plus c? Well, you can, and look what happens. So I've got 3 terms there. I'm going to make the evaluation from 0 to pi over 4. Okay, so I'm putting pi over 4 in first. Tangent of pi over 4 plus pi over 4, and then we'll put the plus c in there, plus c. Okay, so that's the evaluation at pi over 4. Then I'm going to subtract the evaluation at 0. So this is tangent 0 plus 0 plus c. Oh, and I almost forgot to use red there. So tangent of 0, if you were looking at the tangent graph, where you just remember it's actually going to be 0. So basically, let's see, tangent of 45 degrees, that's what that says. If you're thinking of the 45-degree triangle, 45, 45, 90, see opposite over adjacent, that's going to be 1. So I have 1 plus pi over 4. We have a plus c. So look what happens to the c, and then we have minus c. That will always happen. And so that's why when I've been doing these and I take any antiderivative, I'll take the antiderivative where c is 0. Because, you know, that's always going to happen. We're just kind of wasting our time there. But, I mean, come on. When you're in a math class, aren't you usually wasting your time? You probably are. So that happens to be the net area of this graph from 0 to pi over 4. And that completes problem number 7. And now it's time to look at the fundamental theorem of calculus, part 1. So here it is. So I did part 2 first because that is the most important one. This one you'll have problems, but the one that better stick with you is the one that we've been doing, how to evaluate a definite integral. So this one's weird. The first time I saw this, I thought it was really crazy. So let's look inside here first, and then we'll take a look at that. Let g be the definite integral from a to x. So a is some number. X is a variable. And then we have f of t dt. So it looks like we switched letters. And your book's going to call the letter t, you know, the variable of integration. Sometimes they call that a dummy variable. Our book actually points that out many times. And so you've got this weird function. And we'll talk about what this function means. If f, this is this guy right here, the integrand, is continuous on the closed interval a, b, this is what fundamental theorem of calculus part 1 says, then g, which is when you integrate from some number to x, is continuous on AB, and g is differentiable on open AB. And here's the kicker right here. It says g prime equals f of x. So g prime of x equals f of x. And so basically this looks very confusing. And all it is saying is that integrals and derivatives are inverses of each other. So what does that mean? That means if I set up my antiderivative gun right there, and you know I have an a to x there, and then I put my derivative gun right after it, and so this little animal gets zapped first by the antiderivative gun, where it's going from a number to x, and then gets zapped by the derivative gun, it just becomes the original function. And now he's walking around with x as his variable instead of t. And so that's all this fundamental theorem of calculus part 1 says. It says the integrals and derivatives are inverses of each other, which we probably already guessed that. So what is this really? So let me go ahead and explain this in terms of the bug talk. So with the bug, we had something called the displacement. And so what I'm going to do is I'm going to write this function called capital D of A. Okay, so that's weird. So that's the number, that's the A we see. And I'm going to call this capital D of A of x. This equals integral from A to x of the velocity function. And I know that looks very confusing, and maybe you said you were going to try to explain this so we understood this. This is something we never gave to you because we didn't really need to do this, but now I'm going to. What is this really? This is the displacement from time A to time x. So, you know, lots of times we start our time at 0, so lots of times we'll say displacement 0, d0x. And so you can put like x equals 7, x equals 12, and each time you plug it into this function, it gives you the displacement from 0 to those times. And it's kind of a neat function. We don't always need it, but it is one way of grabbing onto the displacement that we never saw in this class, where we wrote it like this. We never did that. Another way of describing this happens to be the net area from A to X, from A to X. So basically what the fundamental theorem of calculus 1 says is if you've got this displacement function and you take its derivative, okay, with respect to x, then what that does is it gives you the velocity function. Okay, so here's the antiderivative gun, and you put the derivative gun in front of it, and boom. It's just like what I said up here. And so that's what it is. Here's the confusing part now. Okay, so like if you're still going, I don't understand this, Joe. We'll do an example, and we'll do it the long way, and then we'll use the fundamental theorem of calculus 1. Okay, so here's the confusing part. Some calculus books call this, what I just showed you, fundamental theorem of calculus 2. And they call the one that we call 2, they call that number 1. So know that these aren't consistent labelings, but there's always two parts, part 1 and part 2. And some books will use fundamental theorem calculus 1. So that's why ours does it first. They'll use this to prove fundamental theorem of calculus number 2. Now the book dwells on an area function. So I've tried to not assign those problems. They should really be calling it the net area function. I've decided to skip it because I don't want you guys getting confused with their so-called area function, which is legitimate, and the net area that we already did. I think there could be area overload if I assign those problems. And it's basically this. They're really doing a displacement from time A to time X. And because I don't want people to get confused come test time and go, oh, I don't know what to do, I've conveniently skipped those problems in the homework. And I've seen other calculus books that never bring up this net area function. And they're just trying to help you deal with this. I think we'll deal with this in our own way. Let's go do some examples. Okay, so our first example of this. So this is fundamental theorem of calculus number 1. Okay, so let's do this problem. Now, here's the fundamental theorem of calculus 1, and I have it written up here, because this one is one that it's weird. Okay, so we just have it written there. Now, before I do this theorem, what I want to do is I want to crank out this problem just like with what we know, using fundamental theorem of calculus 2. So I'm going to ignore this, and I think it's worthwhile. This is where you're going to really go, oh, I see what just happened. So we have d dx, and oh, let me circle our original function. So let's just remember, hey, there's our original function. Circle it in yellow. Okay, let's integrate this guy, or let's take the antiderivative of this. So this is going to be t to the third over 3. Okay, that's the t squared, and then we also have the 12 there. And then this gets evaluated from 1 to x. Okay, so we are actually doing the other fundamental theorem to do this. Okay, so this is really d dx. And on this, we'll just rewrite this as 4t cubed. Evaluate it from 1 to x. Now, when you do your homework, you probably don't want to do all this. In fact, sometimes you can't even compute the antiderivative. And so we're kind of showing you something here. So I plug x in, because now I'm doing fundamental theorem of calculus 2. And this derivative gun is just waiting on the outside. So I plug x in there for t. So I have 4x cubed. And now I plug 1 in. And when I plug 1 in, I get 4. So I'm going to go minus 4. Okay, so that just takes care of this integral from 1 to x of 12t squared dt. So look what happens. Now I'm going to take the derivative with respect to x. And the first part gives me 12x squared. And the derivative of 4 is 0. So there's our answer. And I want you to take a look at this. Look at that. Doesn't that look the same? Except now it's not a t anymore, it's an x. And isn't that exactly what fundamental theorem of calculus number 1 says will happen? You line up the derivative gun right outside the antiderivative gun. They're inverses of each other, you'll end up with the same thing. Okay, now I know some of you were annoyed when I did this on the other problem, but I'm going to go ahead and do this again. This is 1.5. So I wanted to show you something. Suppose this problem had integral, so it's going to almost be the same problem, but I'm going to go from 2 to x, 12t squared dt. And you know what? I can circle that in yellow as well. So we probably already know what's going to happen. Let's just go ahead and crank it out the long way, not using the fundamental theorem part 1. Okay, so I will use the fundamental theorem part 2. So this gives me dx, and I know this is going to become a 4t cubed. And this gets evaluated from 2 to x. Okay, so we end up putting x in, so that gives me 4x cubed, and then we have minus, let's see, 2 cubed, which is 8 times 4, which is 32, so this is minus 32. And now I'm taking the derivative of that with respect to x, so I end up getting 12x squared, and then the derivative of a constant is just 0. So here's the scary part about this, is it doesn't matter what real number is down there. You know, there was a 1 there and a 2 there. You know, the next time we could actually put a pi there or a -7 there. It doesn't matter where the displacement, where the time interval begins with. As long as there's an x up there, you'll always get the integrand, but with the different letter, with whatever letter that is. And so that is what we're going to do. So now, when we start doing some of the other problems, problem number 2, we're not going to go ahead and take the integral. We're just going to jump from here to the answer. Okay? And we could have done that from here. We could have said, oh yeah, it's because I have the derivative gun and the antiderivative gun, and so I'm just going to get the same thing, whatever this letter is. Now, I want to show you one more thing. So, I know, is this bad planning on my part? Yeah. You can turn off the video anytime you want and say, I don't want to watch this. It's a free country. Well, sort of. Except you have to shelter in place. And I think tomorrow you can't go to the beach if you live in California. So, yes. Besides that, it's a free country. So, suppose, you know, some of you were probably wondering this. I went ahead and I said, let's take the integral from 1 to 3, 12t squared dt. Okay, and we'll circle this. So what's different about this? The difference is this integral here does not have a variable x. It just goes from 1 to 3. So we'll go through this quickly here. Notice the fundamental theorem of calculus 1 has a variable on one of those limits of integration, on the top one actually. Let's see what happens when you just put numbers in there. And some of you already know the punchline to this joke. Is this a joke? I don't know if it's a joke. 4t cubed This gets evaluated from 1 to 3. So this is where you have the derivative gun ready. And so what do we have? We have 3 cubed, which is 27. 27 times 4. I think the last time I checked that was 108. Let me just double check. 27 times 4 is 108. And then we go minus, and we put 1 into that function. Oops, I smudged it. Smudged the ink. I didn't smudge the calculation. And so look what I end up having. We have the derivative with respect to x of the constant 104, which gives us 0. So was this fundamental theorem of calculus 1? No, because there was not a variable x up there. There were numbers there. And so we could have said, oh, well, that's just going to give us a net area, which is a real number, and the derivative of a real number is 0. So this fundamental theorem of calculus 1 is not as popular as the one that we do, where in fact, we are doing fundamental theorem of calculus 2 whenever we evaluate a definite integral, and we put this line up and we do that. But let's go do some problems where we can't do it the long way, which is actually a good thing. Okay, so here it is. So I have fundamental theorem of calculus 1 right there, and we are supposed to do this. So basically, these problems, even though I've assigned, you know, you might go, oh man, he assigned a lot of problems, they're pretty fast. There's the function right there. That's this guy right here. And when you have this set up, well, there's a number there, there's a number there, and there's an x there, and a dx there, you're going to end up just getting your function, because you have your antiderivative gun and then your derivative gun. And you're going to get this function in yellow, but now it's going to be written in terms of whatever this letter is. So this is going to be x squared all over 1 minus sine of x. And that completes the problem. They almost sound like dumb problems, and we're actually going to show you the use, you know, the applications in the real world for this. They almost sound like kind of dumb. I mean, look at this. I'm just writing this, but it has x's in it. But that is the fundamental theorem of calculus 1, and we're done with this problem. Let's go ahead and do the next problem. Oh, by the way, if you were like, I'm going to do this the long way and find out what the antiderivative of this is, good luck. We don't have enough skills to find out what the antiderivative of that thing is. Does it have an antiderivative? Yeah, but we haven't even learned U substitution. So this is the only way of doing the problem. Okay, problem number 3. Oh, now this one does have a twist in it, okay, because some of you might have noticed. Well, what's up with this? There's the function there, and you know, we have that right there. Some other things that we might notice is this, in order to use fundamental theorem of calculus 1, it has to look just like this setup, where the number is on the lower limit of integration and the x is on the top. And oh, we don't have x now, we have w, but that's all right. But that's on the bottom. So I don't know if you remember how to change this. When you switch the limits of integration, if you remember that property of integrals, what it does to the integral, it actually puts a negative in front of it. So I used to have t's on the inside in some of these problems, and now I have x's on the inside. So it doesn't exactly match that, but okay, playing the role of t is x, and playing the role of x over here is w. And so this is what we're taking the derivative of. Okay, so now I have this set up where I can do fundamental theorem of calculus 1, and this is the function that's going to get replaced with, well, actually, let's bring this negative out front. I know this is a small detail, dw. I can bring that negative out in front of the derivative, so I have 0 to w. And we have this right here. Okay, so this right here is what we're going to be doing fundamental theorem of calculus 1 on, okay? And so now this is going to get replaced with this function, but written in terms of w's. So we have minus the square root w squared plus w. So did you see how I had to get it set up so the constant's on the bottom and then the variables on the top, so it matches this theorem? Of course, I should be putting equal signs, and so that's how I did the problem. Now some of you are like, well, if I had a few of these to do, I might be able to just jump to the answer because I could see that that's going to put a negative there. And yeah, maybe that's the case. Let's go ahead and do another problem. Okay, so this one is different. This one's different because instead of having just an x on the top, we have an x squared. So we're not really sure how this is going to work. Okay, I mean, you might have a good guess. When I'm going to do this, I'm going to do this the long way. Okay, and then we'll get another one that will do it the shorter way. Okay, so this is the long way of doing this problem. And so how am I going to do this? Well, I'm going to just write the d dx out front, and I'm going to take the antiderivative of e to the t, which is e to the t. Okay, and that's going to get evaluated from 2 to x squared. Okay, and then we're taking the derivative of that. Okay, so the derivative with respect to x, let's do fundamental theorem of calculus 2 on this. So we are putting x squared in there, so I have e, and where are we putting that? We are putting it in for the t, so this is e to the x squared minus e squared. Okay, so that is what I did. Now I'm going to go ahead and take the derivative. The derivative of the first is e to the x squared, but this is a chain rule, so I have to take the derivative of x squared, which is 2x. So this is chain rule. And the derivative of e squared, you know, some of you might say, oh, that's 2e, but remember, this is all a constant, so that's just minus 0. So if we clean up the answer nicely, we end up getting 2x e raised to the x squared power. There's our answer. So what happened here? What happened is, you know, notice how it looks like you just write f of x. Well, now you're going to write out wherever the t is, you put that x squared there. Do you see? And so if it was x to the third, it would be e x to the third. And then what sits out here is the result of the chain rule. So this is the result of, oh, my ink is falling off, of the chain rule. And this is the derivative of x squared. Okay, so on the next one, we're not going to be able to find the antiderivative, and then we're going to see if we can do the chain rule when we do this. So let's do this. Problem number 5. Okay, so there is the fundamental theorem of calculus number 1. And I don't know how to take the antiderivative of tangent x. Now some of you are like, yeah, we do, we learned that, but that is the derivative. The antiderivative I don't know. So this is what I'm going to do. I'm going to write out tangent. So normally you would say, oh, that would be tangent x, because we see an x there, but it's going to be tangent of what? It's going to be tangent of whatever this is. So I replace the theta, just kind of like what we did over here. We replaced the t, excuse me, we replaced the t with the x squared. And then we took the derivative of that, because that was the chain rule. So that's what I'm going to do. I'm going to replace the theta with x cubed. We don't need parentheses, but I'm feeling a little insecure today, so I'll put them there. And then this is the result of a chain rule. I'm going to take the derivative of the x cubed, which is 3x squared, and I'm going to multiply that by that, and this gives me the answer. So this is how we do these problems. Okay, let's go ahead and do problem number 6. This will be our last problem with fundamental theorem of calculus number 1. And we'll see how we do with this one. So I don't even have the theorem written up there. I have the variable on the bottom. So I'm going to go ahead and switch that by putting a negative out front. And now this goes from 2 e to the z, 2 to e to the z, and then we have sine cubed t dt. Okay, so what we're going to do is we're going to rewrite this. This is the one I was circling in yellow. Maybe I should circle it in yellow again. And what I'm going to do on this is I'm changing to the variable z. So this is going to be sine cubed. And instead of putting a z there, I'm going to write e to the z. Okay, so that's the yellow part. Now, because it wasn't just a z there, I have to do the chain rule when I'm doing this, so I got to remember to put an e to the z there. And then, don't forget your negative sign. And so that is the answer. Now I know that we've had this theorem that we're using. Let me go ahead and try to write this up when you do have to use the chain rule, okay? So I don't have a book in front of me, so I'm just going to kind of, hopefully I don't get the wrong answer. So when you have, it goes from a to, let's just write this as h of t. And then this says f of t dt. So when you do this, you are really going to go f of h of t, and you're going to do the chain rule, so you're going to go h prime of, oh, okay, I'm sorry. So it's because I'm making this up on the spot, and I'm not, am I really making this up? This should say h of x. Okay, so h of x, a to h of x. So this is going to be h of x. Okay, so that's kind of what we're doing here, except, I mean, this is all messed up because, why is it messed up? I mean, this is probably a better example, you know, when we had the t there and we had the x there. And then, so, then I'll go h prime of x right there. So I think this is the fundamental theorem of calculus, part 1, when you have an h of x there instead of just an x. And you can see that that works. We went f of h of x. So this right here is f of x, f of this guy. So this is e to the x squared. And then we went the derivative of h of x. And that gave us the 2x. So practice some of these in your homework. The chain rule ones are a little tricky. You just have to rewrite this function, but oh, okay, so from here you just have to rewrite this function, and wherever the t is, you put whatever this is, and then you have to take the derivative of that and put it out here, because that's the chain rule. Okay, so of both of the theorems, we have fundamental theorem of calculus 1 and fundamental theorem of calculus 2. So there it is. Those are both of them. The more important one for you guys as you continue through calculus is this one, because this one tells you how to evaluate a definite integral. This one, you know, it's a little crazy. It's like, why are we doing this? It seems stupid, actually. Fundamental theorem of calculus 1. Well, I'm going to actually show you some functions that are used maybe in statistics and physics. And so here it is, the error function for statistics. Okay, so we have the error function for statistics. I don't even know. Oh, I have that somewhere here. Oh yeah, and it's also, you know, this is used in science as well, and that's what ERF stands for. ER for error, and then F function, error function, and it looks like this. It looks like 0. That's not 0. 2 over root pi, 0 to x, and then we have this right here. Now this is very hard to take the antiderivative of. In fact, you might need something called infinite series. And this is what you're looking at in statistics. And there are times when you have to take the derivative of this with respect to x. You will be doing fundamental theorem of calculus 1. And so there's one example of this in the real world that is used a lot. Another example from physics comes from a guy named Fresnel. I want to say Fresno, but I don't think he was related to Fresno, or if Fresno was a person, I know it's a city. So this guy lived from 1788 to 1827, and he was studying the diffraction of light waves. So this has everything to do with light waves. And so he would use this, and sometimes you would have to take the derivative of this with respect to x, in which you would do fundamental theorem of calculus number 1. The funny part about things in math is this was used for light waves, but more recently, this was actually, they found another application that's related to the design of highways. So there you have it. We have the fundamental theorem of calculus 2, which is the most important one, where you can evaluate a definite integral. And then you have fundamental theorem of calculus 1, in which you're taking the derivative of an integral, and you end up with the integrand, but with a different letter. And so that completes this section 5.3. Keep up with your homework. We only have a few more sections till the end of the class. Have a good day.